Share screen. Okay, okay, I'll turn off my video so it doesn't slow things down. Okay. So last time, oh, no, that's not what we're doing. To do it later. I want to cover the flip-flop gate. Let me if you could give me 1 second. We're going to do iCloud keynote, and it's lecture 17. Right, it's last slide of lecture 17, I think. I thought it was 18 and 19. Okay, class 17. No, where is it? Class 17. Sorry. Okay, so we covered the controlled input. Okay, here it is, class 18. Sorry about that. And now we're going to learn what is called a flip-flop gate, right? The flip-flop gate, as I mentioned, just generally, is a way to store a single bit of data, right? So let's see how it works. Please let me know, do you see the spinning circle?
Yes.
Yeah.
Okay. Yeah, I turned off my video feed to like just remove the load from the data. Okay. So the flip-flop gates is going to have 2 inputs, set and reset, or we're going to call them S and R. Okay. All right. So this is what is going to look like. Okay, just,
Is this the type of gate that's used in a computer to like reset the computer?
So the meaning of set and reset here is not intuitive, right? What it literally means when we talk about it is S set would set the register for that bit to 1, and reset would reset it to 0, right? So we're going to look at several versions of the flip-flop gate, including the one that is connected to the clock, which is what it is like in the real computer. The clock is the system clock is involved, and we're not talking about the clock that counts, seconds and minutes. This is the internal clock that flips like a billion times a second. And if you recall the very first lecture, right, where I had a diagram of what it looks like, the internal clock of the processor. In any case, if you think of a bit, right, what are the 2 possible states for a bit? Any bit?
0 and 1.
0, 1, right? So when you have a gate which is supposed to store it like memory, if you set signal to S, it will set that bit to 0, and when you send signal to R, it should set the. I'm sorry. When you send the signal to S, it will set the bit to 1. And if you set a signal to R, it will reset that bit to 0. Now, let's see how it might work, right? Our flip-flop gate, has those 2 inputs, but it also has 2 outputs, Q and Q prime, right? And it's a sort of duplicate thing where Q could be either 1 or 0, right? But whatever Q is, Q prime is going to be its complement, right? So when we have our truth table, we have the 2 inputs, we have the Q, the output, and then sort of maybe redundantly, we have the complement of the output, right? So why do we need this complement? And the other sort of like side of the same question, the flip side of it, is that what is weird about this circuit? It looks generally a lot like some of the other circuits we've seen. I see some OR gates, actually, with the little circle in front of them. What does the little circle do? The OR gate with the little circle in front of it. What do we call that?
NOR?
Doesn't it complement?
That's right. Both students are correct. the little circle complements the value, so it's NOR with the not after it, or NOR, right? So both students are exactly right. But what is weird, we've seen all of that before. What is weird about this circuit, and it is a little bit related to the fact that we have both the true output and the complementary output.
The NOR gate's input takes the output of the other gate.
Of itself, yeah, that's right. That's exactly right. This circuit has feedback, right? It backs, it feeds back into itself, like the snake eating its tail, right? So that is a little bit unusual so far. Now let's see how it works. Right? So we start with no signal, right? So before, we just put it into the circuit board. We haven't turned it on, so there's no signal going in S and no signal going in R, so both inputs are 0. Okay. Now then, if we assert that this flip-flop circuit will store a bit of data, that means that it has some kind of present state, right? We don't know what it is. Could be 0, could be 1. And what we want to ascertain is that whatever the present state is, without us sending any signal to either S or R, that present state should be able to persist, right? Should not change. So let's, or present state, previous state, yeah. Let's see what it might, let's just trace it, as it were, right? We have no signals on either of the inputs. That means that S and R are both 0, which is going to be the first tuple of our truth table, the first row. Okay, so if S is 0, right, and then let's assume that the other one is 0 too, right? Everything is 0, right? If S is 0, then let's see, then this becomes 1. Then this becomes 1, and this is 0, right? So together they're going to be 1, and if we knot them or complement them, they're going to become 0, right? And its complement are going to be 1, right? Why? So if this is a 0, this is a 0, and this is a 0, together they're 1. I'm sorry, they're 0, and the complement of 0 is 1. And now that we have sort of gotten this outcome, as it were, Q is 0 and Q prime is 1, right? We can keep circling as many times as we want, and it's not going to change. However, if the present state of Q was 1, right? So if present state of Q was 0, it stays 0. However, what happens if the present state of Q is 1? So let's go. We go 1 from Q, goes here. S is 0, so 1 and 0, 1 or 0 is 1. The opposite of 1 is 0, right? Then we follow it here. 0 or 0 is 0, and then complement of 0 is 1. So if the previous state of Q is 1, the current state of Q is also going to be 1. Right? And then, so if Q is, again 1, we go back. It's 1, or 0 is 1, complement of 1 is 0. So basically, if Q was 0, it stays 0, and Q complement stays 1. If Q was 1, Q stays 1, and complement of Q stays 0. Right? So to express that, we just say PS. We don't. So for this first row, we're not going to say 1 or 0 or 0 or 1, but we're going to say PS standing for previous state, meaning that as long as we don't send any of these signals, it's going to remain previous state, whatever it was. Any questions about this? And we already see that by virtue of that, it's already storing the previous state, right? So unless we start sending one signals to either S or R, the state is not changing. So if that bit had stored 1 in it, it would just keep 1. If it had stored 0, it'll just keep 0. Again, any questions about it?
Wait, so not Q is storing, or?
The whole circuit effectively stores the bit.
Okay.
The Q and the Q prime are the outcomes, right? And they're, obviously they're always opposite of each other just by design. And the sort of like the importance of this is that as long as we don't send either a set or a reset signal, whatever the previous state was, it's going to remain unchanged.
So
right? We can keep.
Well, if the previous state for Q was 0, then the previous state for not Q would be 1?
That's right.
Okay.
But if previous state for Q was 1, then the previous state for Q complement would be 0, right? And that the only reason we need the Q complement output is in order for the feedback, for the whole thing to work effectively, because like ultimately, if we want to read the bit, we would only read the true value. We would read the Q, right? Which could be either 0 or 1. I don't know if that makes sense. Okay, well, let's go forward. Maybe it'll become clearer, right? So now we're going to look at two possibilities where we send either a set signal or a reset signal. So the first one is we're setting the reset signal. So S is 0, R is 1. Right? So if S is 0 and R is 1, let's see what happens. So R is 0. I'm sorry, R is 1, so R goes into the OR. Whatever is the second input for the OR, the output of the OR is going to be 1. Okay? And the opposite of 1 is going to be 0. And this is what we wanted, right? We send the signal to reset, and we want Q to be 0, right? So now, whether or not the previous state was 0 or 1, sending the reset signal will reset this thing to 0. Reset means set to 0. And then if we keep sort of like spinning here, let's see that it will stay like that. So 0 goes in here, right? And then, of course, sets, there was no set signal, so both are 0. So the OR gate output is going to be 0, and the complement, the inverter, will make it 1. Right? So we're good. Q is 0, Q prime is 1. And then we can keep going, right? So this 1 can go in here. The reset is still 1. This thing is still 1. Inverted 1 is still 0, right? And then we just can go round and round and round. And now that it resulted in the 0, it will not change by itself.
Sorry, Professor, I'm a little bit confused. How do we know what the value is for the second value going into the Q?
The second value is not going into Q. It's so actually, that's a great question. So let's look carefully at what's happening. So we know that the empty white circle is the inverter, right? But what about the black? We know that, right? What about the black dot? What does the black dot mean?
Black dot's just indicating that split, yeah.
So the black dot is the splitter, okay? So what this means is that when you have a signal, whatever it is going to the black dot, it just splits it. So one half, well, not half, it copies it. It makes two copies effectively, right? So, one of those goes into Q, right? So if we have 1, 1, 0 goes into Q. But the other copy of that 0 goes back, right? And it enters this OR gate along with the S, which is 0. So we have two 0 inputs, produce 0. Inverter makes 1, and it goes here. Here it splits. 1 goes into Q prime, as it should, and it also goes back here. And goes back into this OR. So we have 1 or 1 is 1, inverted to 0, right? So,
but that's my question. How do we know that? Because we put in 0 for S and 1 for R, right? But how do we know not Q is 1 when it goes into the NOR for 1 and 1 NOR?
You're saying like the first time around, right? The first time around the block, how do we know? Is that the question?
Yeah, like we have 0 for S and 1 for R.
Right.
R is taking in not,
right.
R nor not Q, but how do we know the value for not Q?
Fair question, right? Can anybody answer that? It's a fair question. Who can answer that question? It's a fair question, but it's a trick question. Yeah, go ahead.
So I know the answer for this particular situation where R is 1, but I am confused about like where R is 0. But for R is 1, anything ORed with 1 is going to be 1, and then the negation of that is going to be 0. So that's how we get to Q. We don't need to know what Q prime is for this particular situation. But I have I'm still confused how, like, about the first case that we did.
Right. So in this case, correct. The answer is correct. It doesn't matter what Q prime was, right? Because this is an OR gate. We get the signal from R, which is 1. It doesn't matter what the second input is. The whole thing is 1, then it becomes 0 and comes out.
Oh, okay.
Now, generally also, we can assume that we can circle through it a few times, right? So if if it's like not immediately clear, from the very beginning, or you can sort of like go through it, once and then keep going, and then it will stabilize at a certain state, right? It will happen, instantaneously. So if there is some kind of uncertainty, like in the first moment, it will stabilize after the first cycle, as it were, and then it will remain stable. But let's see. So Anna, I think, asked, well, how about the previous situation, right? The previous situation that we already went through. I guess I'll go back and I'll catch up real quick. And so here we have the previous state that maintains, right? And then, Anna, just to confirm, you're asking about S0 R1. Is that what you're?
Yeah.
No.
Yes.
No, you're actually asking about the next one. You're asking about S1 R0.
Either or, like where
we just did.
0.
So right now we did S0 R1, right? And with S0 R1, we didn't need to know the present state at all. Was that clear? You answered the question, right?
Right. For the second case, yes.
Well, the third case where S is 1 and R is 0, yes? I just want to make sure that I'm answering the right question, your question.
I'm still trying to like wrap my head around where S is 0 and R is 0, not the other ones.
Okay, yes. Okay, so we're going to go over again the previous state situation. The previous state meaning that both S and R is 0. And what that means is that this thing has not been even turned on, right? Or no signal has come into this bit. This bit is just sitting. Nobody is talking to it, so whatever garbage whatever garbage value it has, either 1 or 0, is just going to stay there until somebody explicitly say, "Oh, set this to 1" or reset it to 0, right? So we want to sort of like ascertain that whatever that unknown state is, it's going to persist. So far, so good, right?
Yes.
Yes? Okay. Well, and as you say, it is possible that present state for Q, let's just look at Q, is 0, or present state for Q is 1, right? Could be either of those things, right? So we're going to split it and have two separate proofs, right? Does that make sense? So first we're going to think, yes?
Yeah, that makes more sense. Yeah.
Okay, but I'll just do it again, just because I think that others may have this, right? So yeah, we don't know what previous state is, but we're going to first test when the previous state is 0 and like be done with that, and then we separately test when the previous state is 1, and then we'll see what. Okay, so previous state is 0. So like this thing is 0, right? So if it's 0, and of course, if Q is 0, then its complement is 1. So we know that Q is 0, complement of Q is 1. Okay, so let's go with the Q. The 0 goes in here, and set is still 0. So 0, 0 makes 0. Not 0 is 1, and that's what Q prime gets. It already had 1, it gets 1 again, right? Nothing changed. So we can look at the feedback from there. Goes here as 1, right? Whether before we cycled or after, right? Still 1. It just goes 1. There is no signal on R. Still 0. 1 or 0 is 1. And I think I hit it. Sorry. I hit it 1 too much. Okay, we're doing the situation when true state is 0 and then complement is 1. So we have the 1 from Q prime going in here. Reset is still 0. 1 or 0 is 1. Inverted is 0, and Q gets 0 again, right? And we can go round and round, 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 and as many times as we want, and it'll just stay Q0, Q prime 1. Any questions at this moment? Okay. And then we say, okay, what if Q is 1? Well, if Q is 1, Q prime is 0, has to be, right? And, the 1 goes in here, 1 or 0 is 1, inverted is 0, and that's, so Q prime is 0, stays as it was, then goes in here, 0 or 0 is 0, inverted is 1, and Q stays 1. Again, you can just keep going and it stays the same. So this is actually, in some way, it's easier to imagine. The following two are a little trickier, right? Because they are supposed to work no matter what the previous state is. Yeah. So in the second row, where S, set has no signal, but R gets a signal, right? That's the second row. We let's see. We should not. No, let's rephrase that. The outcome should be the same, independent of the previous state, right? So with 0, 0, previous state stays the same, whatever it was. But with 0, 1 or 1, 0, the present state may stay the same, or it may change depending on what it was. What is guaranteed is the outcome. Okay? So I'll just go over it again. We have still 0 on S, no signal there, but we get R here. We get R1. So because we don't know what Q and Q prime are at this point, we just don't know. Could be either, right? We only right now are going, just to keep things simple, what we're only certain of is that R, well, we're certain that S is 0 and we're certain that R is 1. So when we do like unknown or 1 is 1, flipped is going to be 0, right? So the Q should become 0. And it makes sense because R reset means reset this thing to 0, right? So this is what we want to happen. And let's just keep going from there. Q is 0, it goes into here. We know S is still 0, so 0 is 0 is 0. Inverted, it becomes 1. So we got to the state as we wanted. We sent a reset signal, and our Q became 0. Now we need to ensure that it'll stay like that, right? So Q is 0, goes in here, 0 or 0 is 0, complement is 1, so Q prime stays 1. 1 goes in here, 1 and 1, and 1 or 1 is 1, inverted becomes 0, right? And now we just can keep going round and round and round, and it just stay like that. Yeah. So by sending the reset signal, setting it to 1, as it were, we reset this thing to 0. Okay, next one. And it's complement to 1, as it should be. Now we're going to cut the juice on R. It'll be 0, and then we'll send the set signal here to S. We send 1 to S. So we have 1 to S and nothing to R. Okay, so 1 goes into S. So we have 1 or unknown is 1. Inverted is 0. Okay, let's just follow from there. 0 or 0 is 0. Inverted is 1. And now we can keep going. 1 goes back here. 1 or 1 is 1. Inverted is 0. And then we keep going. 0 or 0 is 0. Inverted is 1, 1. And we can just, again, keep going round and round and round, and it'll stay the same. So that's the idea of the flip-flop gate, a set-reset gate, where when there is both zeros, we maintain the previous state, and then we can force it to go either to 1 or to 0. Right? So these are the 3 possible outcomes: previous state, 0, 1.
比如说你这边，你像工作1个月4、5千，你买一个香奈儿的包，也是4、5千，就是相当于是你在这边生活1个月就可以买香奈儿。然后现在但香奈儿的包
I think somebody needs to turn off their mic, right?
几万块钱，就相当于怎么说
？What is that?
1个月就可以买一个香奈儿的包，就是平均工资，我只说的是平均工资，还不包括那种稍微高一点的或怎样的。就是你
Yang Chen, you must turn off your mic, otherwise I have to.
因为香奈儿的包全球定价都差不多嘛。
Professor, I think you can just mute them.
Can I don't see the mute button. I basically had to remove him from the session. I have pin video, send a chat message, make moderator, make presenter, make caption.
I don't think it shows mute if they're not unmuted, but because I'm unmuted, for instance, now you should be able to mute.
Yeah.
Okay, let's see. Okay, now I see it. Oops. All right, he'll have to watch the video. All right. Okay, you learn something new every day, right? So, okay, let's go back to that lecture. We still have. Ooh, we don't have time. So we're going a little bit over, but if you cannot stay, raise your hand, or like I'm recording this. I'm sorry that the previous class ran long, so I'm going to try to finish as soon as I can. But I want to just finish this, gate. Like I need to finish it today. So if you can stay, just raise your hand. But I promise to finish in the next 5 minutes. Okay. Where are we? So this is important. They sprang up this other class on me in the last minute. This was supposed to be the only one I teach this session, but yeah, you have to do what you have to do. While it's loading, please ask me more questions.
So just to make sure I'm understanding right with the flip-flop, essentially we need to do the base case where we get no input just because we have no idea what Q is going to be, but after that we should be able to determine it because when we get an input from S or R, it should always have the same output. Is that right?
Yes. So you're saying, why do we care about the previous state? Why do we need to consider that situation? Because you say that afterwards, we set it to something definite, and then, we know. So the observation is sort of correct, but then the conclusion is not quite right. Let's say that we sent a signal to this thing to, let's say, I don't know. First we, reset it to 0, and then we sent another signal and we set it to 1, right? And now it's set to 1 and it's sort of like definite. But then let's say we walk away, right? It should keep that value, right? So the point of it, okay, here's the thing. The point of it that as long as we don't send, as long as we don't send any other signals to either S or R, right? That would be the situation with 2 zeros, right? We let's say that we set it to 1, yesterday, right? And then we didn't send any more signals for 24 hours. Then I came back and I don't remember. I don't remember I don't remember. Did I make it 1? Did I make it 0? Well, that's okay. I can still, look at Q, right? Until I send any more signals, Q is going to be what it was yesterday, right? So in fact, I have memory. My bit now remembers its state, and I can check it later. Does that make sense?
Yes, that does. Thank you.
Okay. So in fact, I don't have to remember because it remembers. Okay, good. So what if both S and R are 1? Interesting, right? If we follow this, then what we'll get is both Q and complement of Q will get 0, right? If you don't believe me. So basically, look, let's say that Q was 1 and complement of Q was 1, right? So, R, we send 1 to S. So this thing, the OR gate is going to be 1 no matter what. The inverter is going to be 0, and then Q prime will become 0. And then we'll send at the same time 1 to R, and OR will make it 1, and inverter will make it 0. And we got a situation where both are 0, and it'll keep like that. So that's no good, right? Well, by definition, because we defined that our flip-flop should necessarily should be Q and its complement. But you say, oh, but what if it happens? And it should not happen, right? Because at every clock cycle, we can only send one signal, either set or reset, right? We wouldn't want to attempt to make this bit equal to both 1 and 0 at the same time, right? That's a Q bit. That's or whatever. The quantum, nonsense. We're working with deterministic circuits, right? Where a bit can be either 0 or 1. So the condition where both are 1 is the won't happen condition, right? So we're like it's a condition that we're going to dismiss, right? For first of all, because we defined just by definition, Q has to be equal to Q prime, right? They have to be complement of each other. And also our inputs should always be complementary in a sense. But if they're not, they both can be 0, that's fine. But if we're sending a signal, we can only send it to one of them, right? So we're going to cross out that whole bottom row. So our truth table will only have 3 rows, which is sort of unusual because usually it's like powers of 2, but in this case it's by, restricted by definition. Does that make sense? Right? We want to have just 3 outcomes. Unknown previous state, which becomes known when we test it on the outcome. It's not that it's unknown. Whatever previous state was, it gets maintained, right? We can, check what it is. It's just that our circuit will not change it by itself, right? And if we send the reset signal, if it's 0, it'll keep 0. If it's 1, it'll reset it to 1. And if we send the set signal, if it was 1, it'll keep 1. If it was 0, it'll set it to 1. Does that make sense? And this is all that I needed to cover today. We started 20 minutes late. I'm sorry we went 15 minutes long. But any questions about this? This is important. OK. If there are no questions about this, you have a single assignment for tomorrow, just this one thing. I would like you to evaluate the following flip-flop gate by giving it a truth table, right? So I want, or essentially 2, right? Or 1, whatever, So basically do the same thing that we did with the top flip-flop gate for the bottom flip-flop gate. Both of these gates, by definition, have to do exactly the same thing. They must, with the same inputs, must produce exactly the same outputs, and they do, right? So I assert that they do. But as you see, there are more than one way to build a flip-flop gate that behaves as a flip-flop gate should behave. And I just want you to trace the one down, on the bottom of the slide and come up with the truth table, which hopefully will be the same. Now, however, in the off chance that it's not the same, what does it mean? Last question. What if the truth table that you get is not the same? What does it mean? What does it mean if this? Well, it means that it's no good, right? So I want you to, test it. Okay. So that's the assignment for tomorrow. Nothing else. Any questions?
In the truth, the shortened down truth table, why do you not record not Q?
Oh, because we know that it's
just opposite of Q.
Yeah, right. Basically, we've checked that, and we capped all of the possibilities that maintain our demand that Q and not Q, are complement of each other, right? And we, nixed this one, impossible possibility where they're not complements of each other, right? So essentially, we've restricted input combinations, right? We will not allow, or we will not build our computer to ever have a situation when both R, S, and R are 1. They can both be 0, or they can be complementary to each other. Okay? So tomorrow we're going to look at more flip-flop gates, specifically flip-flop gates integrated into the system clock. Again, if you don't remember the system clock, go to the very first slide set. I think it's like slide number 4 or something like that, where you see it looks like that, right? Obviously, I'll talk about it again. I'll remind you tomorrow. Okay, if there are no more questions, please take a screenshot of this slide. Please take the screenshot of this one slide right now. I will post the whole slide set also now, but just so that you can work immediately. Please take the screenshot of this slide right now, and that is the only homework. Anybody needs to talk to me privately in office hours? Okay. In that case, I stop recording, and I will see everyone tomorrow.
Actually, yeah, I'd like
yes
to ask you a question about the midterm in office hours.
In office hours.
Yeah.
In the office hours. Okay. Okay. So I'll make an office hours session. Okay. Bye, everybody.
Do I just stay here, or is there another one?
No, you have to exit, wait like 30 seconds, refresh it, and you'll see a new session called office hours now.
Okay.